All right, today we start the public key encryption system and RSA. But before that, just a quick question. No? What's the problem with conventional encryption? Okay. Okay, yeah. One of the problems is key sharing or key distribution. Any other problem? Conventional encryption system. Any other problems or issues with conventional encryption? It has too many keys. The number of keys in the system, the total number of keys in the system is way too much. How many keys do you know are in a conventional encryption system? The number of users times number of users minus 1 divided by 2. So if there are 10 of us, and each one of us needs to talk to the other 9 very confidentially, then I need to share a key with each one, a separate key with what this user, that user, that user. So the total number of keys that need to be kept and maintained securely in the system is 10 times n minus 1 divided by 2. So for 10 people, they need 10 times 90, 45 total keys. In order for each one can talk and has a share only a key with only one other person. And that's reasonable, 90 or 45. But when we have a company of 5,000 people, it's going to be a huge number. 5,000 or let's say 10,000, that's 10,000, about maybe another times 10,000, that's 100 million divided by 2, that's 500,000 keys. That's a lot of keys to share or to maintain in the system. That's another problem with conventional encryption system. So conventional encryption system has one problem is how to distribute those keys, and especially when you need to change them frequently, then you have to keep distributing them. It's the large number of keys and the key distribution are two major issues. Are there any other problems or deficiencies in conventional encryption systems? Is there anything that it cannot do that other systems can do? Other little deficiencies: it cannot provide authentication, it cannot provide digital signature, because there are two people who have the key. You cannot be certain who sent that message. You can never be 100% sure if you receive the text, an encrypted message, and you want to prove you sent it or you sent it. They both have the key. Anybody could have sent it. So you can never pinpoint it to one person. And that's authentication is not possible. And consequently, digital signature is not possible using conventional encryption. Okay, so keep that in mind, and that's why they started looking for an alternative, a different system that will solve those deficiencies. So let's start public key encryption system. The public key encryption system, it's based on a mathematical idea, is that if you have two keys or two numbers that can be applied into a formula to encrypt or decrypt or to change a value and bring it back in such a way that it can still remain secure and safe. And they found this idea, this formula, that it would require two numbers. And once those two numbers are generated, if you see one of them, you can never work out, you can't easily work out what the other number is. But if you take data or some number and apply this, one of those keys, we call those keys, they can easily be generated, again mathematically. But if you apply one of the keys in a formula, it will change whatever the data is. and it cannot bring it back. The same key cannot bring it back. You need a second key, this other number that we generated with this, that if you apply to the same formula, but to the new cipher message, it can bring it back. So now we have two keys. One will do encryption, and the other one will do decryption. We're not using the same key. This is the basic idea of public key encryption system. It's just like having a lock or a door or a safe, that you can take one key, unlock it, and you cannot unlock it with the same key. You have to bring the other key to open it. So one will lock, the other one will open. And these two keys will do each other's work. So if this key, it does the locking, it cannot unlock, only this key can unlock it. So the idea is simple. Two numbers, one of them will do the encryption, the other one will do the decryption, or vice versa. Maybe the first one can encrypt and the second one can decrypt, as long as you have those keys. Now the idea, those two keys are easily generated. So we'll find out later on how to generate them and how to do the actual encryption algorithm. So you generate a pair of keys. In 1 second you can generate a pair of keys that are related, strongly related together, but we cannot see the relationships between them. It's very difficult. If one of them is missing, you cannot work out from this key what the missing key is. And that's an important point. So one important characteristic of those two keys is that if you see one key, you can never work out what the other key is. Either one of them. And the other main characteristic is if we apply this one to encrypt or lock, only the other one. There's no other key in the world except the other one that was created with it. I call them twin keys. So those twins, one of them will lock and the other one unlocks, or vice versa. So this is the characteristics of those two numbers. Seeing one of them, you can never tell what the other, or work out or calculate what the other number is. And the other point, either one of them will do the locking, the other one will unlock. Now, once they worked this out, they said, okay, now to implement it, this is the way it will work. Create a pair of keys, and if you don't like them, you can create another pair. There are millions and billions of keys, of numbers, that can easily be created. So you can create a pair. Let's say you created those two pairs, this pair of keys. Now, they say, keep one of them to yourself. So I'm going to keep the red one. Nobody will see this except me. And we call that's my private key, and this is my public key. And this is where the name public key encryption came from. So everybody can generate a pair of keys and can tell us what their public key is, and they hide their private key. So this key is no longer a secret key. Now, if you want to send me a message nobody in the world can read except I, then you can look up my public key, and it's not secret. If you want, I can send it to you. We have public key directories, like telephone directories. You can put my name and you get the public key. My public key is just like a phone number. Or there are many ways. We'll look later on how we can actually distribute those keys. But they are not secretive keys. That's the good thing about them. They are easier, a little bit easier to distribute than the other keys, the secretive key, that in the conventional encryption system. Now, I can have it on my email. Every time I send an email to somebody, I say, here's my public key. It's always there, my signature maybe, or on my website, or in my documents. It doesn't matter. It's always available. So you can get this key and use it to lock that message, encrypt that message you want to send me. Who can read that message? There's no other key in the world that can unlock it or decrypt it except this key that I have, that no one else in the world has. So everybody can get a copy of that encrypted message. They'll never be able to read it. When I get it, I can read it. And this is the simple idea of public key encryption system. And that's how the message can be confidential. That means nobody can read it except me, who have that private key, provided you use my public key. Okay, so that the idea is so simple. If you want to send a message to anybody, we all have a pair of keys. Every one of us has a pair of keys. At least you can have more than one pair of keys. Many companies and many individuals can have many, and you use one of them to communicate with somebody and use another one to communicate with someone else. It's just like phone numbers. You can have multiple phone numbers as well. But anyway, so if you want to send a confidential message to somebody, which key would you use? Now, this is the problem. Your options are 4 keys. You have a pair of keys and I have a pair of keys. Which key would you use to encrypt? Which key should be used for encrypting the message, and which key should be used for decrypting the message? That's something you need to know. And it's simple. And yet, a lot of students have a lot of problems with it. So just get the logic of it correct, and you should have no problem. And the simple logic is 2 points you need to know. If you want to send a message to somebody, if it's confidential, use the receiver's public key. Of course, I'll say use the receiver's key. Which key would you use? My public key or my private key? Just remember, logically, you don't have access to my private key. Nobody can see my private key, so it's easy. You can only use the receiver's public key. So if I ask you which key would you use to encrypt the message, don't tell me the receiver's private key. You don't have access to that. You only access the receiver's public key. Now that's how simple it is. So all you need, for example, if you want to send a message to Mr. X, all you need is Mr. X's public key, not private key. If you have it, then you can encrypt the message and send it. Everybody can get a copy of that encrypted message. They cannot read it. The only person who can read it is the person who has that private key. So it's your responsibility to keep your private key to yourself. Never give it to anyone. Not to your friend, not to your husband or wife, not to your partner, not to your boyfriend, nobody. Not your parents. That key should be kept just by you. So that's the simple idea. Now, as well as this, I'm going to ask you a question. If I take a message and I encrypt it using my public key, a message, a file, document, and I encrypt it using my public key, who can read that message? Only I, because I am the only one who has the private key that can decrypt it. That's how a lot of companies make their files secure. So if you want to make your file secure in your laptop, that's all you have to do. Generate a pair of keys, they're both your keys, encrypt all the sensitive messages or files or data on your computer, encrypt it with your public key, so even if you lose your computer, nobody can read that information. It's all encrypted. And whenever you want to read it, you produce your private key, decrypt that file, read it, work on it, edit it, do whatever you like. Before you leave it, encrypt it again with your public key. And this is actually a legal requirement. If you work for any organization or any company in Europe or America or Canada, and you have data on that computer, on that laptop, you're not allowed just to have it in its pure format. You must encrypt it. So even if you lose the laptop or the computer, other people find it, they cannot read that information. All right, so that's one thing. If you want to make information confidential for you, confidential and secure, or in your organization, you can write an application that says, okay, where's our sensitive files? They're in this directory. Encrypt everything. You don't even give the staff the key. And then staff member, once they identify themselves, you can decrypt the file and give it to them. When they send it back for storage, encrypt it and put it back. So that can be a project you can have to keep information secure in an organization or on a laptop or on a PC or something like that. Now, the other thing, what if I take a message and I encrypt it with my private key? And I send the message out. Who can read that message? Whoever has my public key. And because my public key is public, then anybody can read it, as long as they get my public key. My public key is available, and we assume they all have it. So if you encrypt a message, if anybody encrypts a message with their private key, and they send it out, that message is no longer confidential. Because anybody in the world can read it, because all they need is your public key, and your public key is public, and everybody has it. But what's so great about this, I know it's not confidential, but if I can take a message and take your public key and decrypt the message, and I can successfully decrypt it, that means that's a proof that your private key was used. If I can use your public key to decrypt it, then your private key was used. And that's the idea of digital signature. So a digital signature, if you can decrypt a message using somebody's private key, that's a full proof that they have encrypted that message. And that's where the non-repudiation comes. Anybody remembers what non-repudiation is? Do you remember what's non-repudiation? You can answer, but I can never hear you. What's non-repudiation? Pardon? Denial of? What's non-repudiation? Are you okay? Are you asleep? What's non-repudiation? No. You cannot deny that you have encrypted a message or sent a message. If you encrypt, is that what you said? Yeah. So if you cannot deny that you've encrypted a message, now we can prove in a court of law that yes, this person encrypted this message. And the judge won't know, but he'll call an expert and say, how do you know? He says, because we can decrypt the message using his or her private key. That means, we can decrypt it using her public key. That means it was encrypted using the private key, and nobody else in the world has that except this person. Well, that's the proof. All right. So the next point, the hint to remember, it doesn't matter who encrypted or where. So I'll be asking you later. This message was encrypted by Alex or Alan. And Bob which key should Bob use to decrypt it? It's the same person. If one person's key, whether public or private, if you use one of my keys to encrypt, if one of my keys was used to encrypt, then the other key of mine, only my other key would decrypt. Keep that in mind. So whoever encrypted the message, if I ask you, which key should we use to decrypt it? Just find out who encrypted it, whose key was encrypted by. By X, Mr. X. Whether it's the private key or the public key, we'll use the other key of Mr. X. So the same person, if one of their keys is used to encrypt, only the other key can be used to decrypt. Don't say, oh, will the receiver then, or the sender. Don't get yourself mixed up. If we use the receiver's key, then the other key of the receiver. If we use the sender's key, then it's the other key of the sender. So the same person who encrypts, also the same person who decrypts. Well, not the same person, but the key that belongs to that person. Right? Just remember that and things will look much easier. But just to check that this is correct. All right, who's gonna help me here? You okay? We're gonna send a message to her that nobody can read but her. That's confidential message. Which key would you use to encrypt? Which key would she use to decrypt? Anybody wants to give him a hand? Want to tell us? Want to send her a message? Which key would you use to encrypt the message? In such a way that it's a confidential message. Only she can read it.
Private.
Pardon?
Private.
Yeah, use private key. That's a missing answer. We have two private keys. Whose private key? Yours or hers? so you didn't hear my first message, my first hint that I gave you earlier. Okay, let me switch to this side. What do you think? Yeah, you want to send her a confidential message? Use the receiver's public key to encrypt. Anytime you want to send a confidential message to someone, use that someone's key, public key. Of course, I don't just say use the public key. There are two public keys. You have two keys, the receiver has two keys, you need to tell me the receiver's public or private key, or the sender's public or private key to encrypt. Right, so you use her public key to encrypt the message, and what would she use to decrypt it? And she used her private key. So, are you with us? No? Can you, right? You want to send him a message, a confidential message. Which keys should you use to encrypt, and which key he should use to decrypt? Yeah? Okay. Okay, so simple, great. Piece of cake, right? Now let's go to the other way. Instead of confidential, now we want an authentic message. A message that we know only that person. It's not necessarily confidential, everybody can read it, but once they read it, they know he actually encrypted that message. So I'm going to start with you. I'm going to send him over there an authentic message that if he reads it, he knows it came from you.
I'll encrypt it with my private key, and he'll encrypt it with my public key.
Very good. Okay, it sounds simple. Does everybody know that? Okay, you want to send me a message, I know it came from you. You encrypted it. Will you send me your private key? Thank you very much. That your private key is no longer private. I know it now. Don't send me your private key. Don't send me your keys. Well, public key. You encrypt it with your private key. And you send me the private key then? Okay. What about the message? You send the ciphered message. That's encrypted by your private key. How would I read it? So you use your private key and I use my public key to decrypt it. I said, whenever a message is encrypted and decrypted, make sure it's decrypted by the same person's key. You can't encrypt with your key and I decrypt with my key. It have to be either both of them your keys or both of them my keys. All right? Do you understand? Right. So you want to send me a not a confidential, authentic message. I know it came from you. How would you encrypt it? Use the private key, right? Guys, if you tell me use the private key or the public key, it's error. You must say the sender or the receiver's private key. Don't just say private key. In an exam, you say private key, you get 0. You need to say the receiver's public key or private key or the sender's private key. Don't forget the word sender or receiver. So if you want to send me a message, I know you wrote it for certain. You encrypted it. How would you encrypt it? Okay, help them out. How would you send me an authentic message? I know it came from you.
And sign with my public key.
Yeah. And how would I read it? So you encrypt the message with your public key. How would I read it? With your private key? I don't have access to your private key. Listen to the answer. Here it is. Yeah? You want to send me an authentic message? I know it came from you.
Encrypted by your public key.
You use my public key to encrypt it.
Yeah, then you encrypted by your private key.
Yeah, but that's anybody can do that. That's not authentic. I won't know it came from you, because anybody else can take my public key and use it to encrypt the message and send it to me. That's called confidential message. Nobody can read it except me. But anybody can do that. I will not know it came from you. Hold on. Shh. Please, guys. the sender's private key. That's your private key.
Yeah, you use the sender public key.
And I use my public key.
Yeah, for the sender, I send to you.
Oh, the sender.
Yeah.
That's you. You are the sender. Don't tell me sender.
Yeah.
What's your name?
No.
Okay, anyway, go on. Security point of view. Hey, Mr. Anyone. Go on. Okay. Which key? Mine or anyone's key? Yeah. But I was a public. Okay. And I use your public key. That's correct. Thank you. Guys, make sure you get this. You get this, the rest of it is so easy. If you don't get it, it will take a long time before you clear it up. All right, so this is the basic idea for public key encryption system, for digital signature, as we will do it later, and for many other bits and pieces that will depend on this simple idea. We're going to look now at how public key operates and how RSA operates, how to generate the keys, and how the actual message is encrypted and decrypted. And then we look at the theoretical aspects of that, or mathematical aspect, and we look at the idea of the prime numbers and co-prime numbers that are used to generate those two special keys. So let's first share this. Any questions so far? All right. So public key encryption system. Symmetric encryption system has a number of issues, problems, and one of them is the total number of keys in a system. Especially if you have a big company with 10,000 users, then the number of keys to use, and remember, we need to frequently change them, or use session keys or whatever, but there's so many keys. So there's always a problem and an issue. Because every couple of people who communicate together, they need to share one key. So this guy at the top here, just one person has key number one with the first person, key number two is second, and so on. So the number of keys is large. And if you were to find out the total number of keys in a company or an organization, it's n times n minus 1 divided by 2. This is in order for each one has a private key, a personal key with each other individual, if they need to all communicate confidentially. And every time you receive a message, you need to find out who you received it from and whose key is that to use. And so it's a bit of you need actual management of those keys. Another complete system of managing those keys, large number of keys. And they need to be kept confidential. And sometimes you don't trust the people that work in, like maybe in IT or other departments, to keep it confidential. They might have access to it, so you need to encrypt them as well. So there's so many other issues involved just with managing those keys. So one way to do it, to distribute those keys, they said let's keep a central place where we can all have only one key with that place, like one person you can communicate with, so you only keep one key. And then every time you need one of the other keys, you ask them, I want to communicate to Tom, and you give me a key that I can use with Tom, or something like that. And so we'll look at key distribution later on. And hence the idea where they said, okay, they thought of public key encryption system. Public key encryption system, in order to encrypt a message, you take the message and you apply a public key that belongs to somebody, someone's public key. You take a message that you can read. Once you encrypt it, it generates this encrypted message. In order to decrypt it, use the private key, or vice versa. So one key is used to encrypt, and the same message, bring it back, use the other key to decrypt it. It could be public key for encryption and private key for decryption. It could be the other way around. It depends whether we want to do confidential communication or authentic communication. So to compute the private key from the public key is difficult. That's the idea. The idea is once you have those two keys created, it's very difficult if you make one of them public, known to everyone, that those people who see that public key cannot recalculate what my private key is. So to encrypt a message or decrypt a message using this system, it's again another mathematical formula. Usually to encrypt a message, you run an encryption algorithm, which is, in this case, it's going to be exactly the same algorithm for encrypting or decrypting. And you use the public key as an input into this encryption algorithm and the message. So to encrypt using the public key a message M, it will give us the cipher message C. And to bring it back, then you decrypt, which is the decryption algorithm, which is pretty much the same. And you decipher the message using the private key or the secret key. So public keys, every time you have a pair of keys, you generate a pair of keys. One of them is the private and one is the public. The public are published. We try to distribute it to other people. Tell them this is my public key. If you want to send me a message, send it to me encrypted on this. So what's the difference? The major difference, but there are a lot more differences between public key and symmetric key, or public key and conventional encryption. By the way, this is called symmetric. That's asymmetric. Now they call it asymmetric, the new key, because the sender will encrypt using one key and the receiver decrypt with a different key. So they're not the same keys used on both sides. That's why they call it the asymmetric, as opposed to the symmetric key, the system, which is the conventional system, which uses both the same key by the sender and the receiver, or the person who encrypts and the person who decrypts. So what's the difference between them? In the symmetric, that's the conventional, the old system, two parties must trust one another. So the two guys who are communicating must trust one another. But if you don't trust somebody and you share a key with them, they might pass it to other people. So then you need to really trust them using the old system, where both sender and receiver must share a key. In order to share a key and keep it, shared and secretive, they need to have some level of confidence in one another. But with the public key, it doesn't matter. You have your public key and everybody knows it, and you don't show your private key. So what they can do with the public key, share it with more people, let them share it. It doesn't reduce security. So you can communicate with your enemy. In fact, you can have a war, with two countries have a war, and their presidents can communicate securely using public key encryption system. Okay, and then both share in the symmetric system. The difference between them, again, in the symmetric system, sender and receiver must share the same key and use the same key. But in the public key encryption system, there are two separate keys used. Either the sender's both keys are used, or the receiver's both keys are used. Remember, the message, if you send me a message, you encrypt it with one of your keys, I can only decrypt it with your other key. If you use one of my keys, then I can decrypt it with my other keys. So. The public key can be used for non-repudiation. The symmetric cannot be used for non-repudiation. It can be used for digital signature, the public key. Symmetric key cannot be used for digital signature. So there are a lot more advantages to the public key. It has less keys, total number of keys in a group is a lot less. How many keys do we need if we have 100 people? Excuse me. If we have 100 people, a company of 100 individuals, and we all want to communicate securely with one another, how many keys do we need if we are using conventional encryption? Or how many keys do we need if we use public key encryption system? For the conventional, it's n multiplied by n divided by 2. That's 100 multiplied by 99 divided by 2, which is 4,500 keys. What about the public keys? How many keys do we need for 100 people in order for them to communicate securely with one another? How many public keys do we need? Okay. 100 keys.
No,
Okay.
200.
Close.
It's 200.
Public and the private.
Yeah. So we need, every individual needs a pair of keys.
Yeah, it's 200.
A public and a private. If there are 100 people in the company, then we need 200 keys. 100 public and 100 private keys. And everybody knows each other's public keys, and then we can send them confidential messages. So see the difference between, in 100 user, 200 total number of keys, while here total number of keys is 4,500 for 100 people. 100 times 99 divided by 2. Okay, some examples of algorithms that use conventional encryption. Now, when we're talking now, we're not talking about Caesar's algorithm or all the other sets, the column transposition. There are modern encryption systems, starting from DES and advanced DES and RC5. There are few Blowfish and few other systems that are in use today. These are the modern electronic conventional encryption system. Like Caesar's is hundreds of years ago, but it's based around the same idea. Which brings me to a question, just a quick question. DES, is DES a transposition or substitution cipher? Is DES a substitution or transposition cipher? Pardon? Transposition. Good answer. That's not the right answer. Pardon? Substitution. Yeah. Another good answer. That's not the right answer. Both. DES is both transposition. All new encryption, modern conventional encryption systems, all the new ones, they use both transposition and encryption to provide a number of properties. Okay, what's the property of diffusion? Diffusion property of an encryption system? Diffusion? Hiding the relationship. Hiding the relationship between what? Ciphertext and the key, right? Is it the key, ciphertext and the key? And the plain text. So hiding the relationship between the plain text and the ciphertext. What about the confusion property? Any idea? Confusion property in encryption systems? Hiding the relationship between the key and the ciphered message. Okay. I just don't want you to forget it quick. Keep reminding you. I'll ask you next week.
Yeah. That's next week.
So this is the idea of public key encryption system. You have a public key, for example, or you get a plain text message, apply the public key to it and pass it through the algorithm, it will produce a ciphered message. In order to decipher the message, use the private key now to decipher it. So use the public key maybe to encrypt and the private key to decrypt, or vice versa. Who's insisting on talking out there, guys? So if you want to run a confidential message, use the public key. You look for the receiver. If you're the sender, you have a message you want to send it to somebody, use their public key. I'm going to start asking people to leave. Please, stay quiet. I don't want to ask you to leave. But I cannot, you and I cannot be talking at the same time. Right, so if you want to send a confidential message, use the public key of the receiver, send them the message, the receiver can use their private key to decrypt the message. If you want to send an authentic message, the sender takes the plain text message, use his or her private key to encrypt it, and the receiver use their public key to decrypt it. And that message is not confidential. Everybody can read it because it's the public key of Bob is used to decrypt it, and everybody has Bob's public key. So it can be used for confidentiality or authenticity. And you could be asked, explain how can it be used? How is public key encryption system used for confidentiality? And this is the system. These are the main components. The plain text message, right here. And the key. And this is the encryption algorithm. But it's important to know which key. So this here, Bob wants to send a message to Alice. So which key should Bob use to send a confidential message? It should use Alice's public key. Don't ever say Alice's private key, because Alice's private key is private to herself. No one else can use it. So Bob, usually, which could be you have a list of all your friends, like phone numbers, but this is public keys. So everybody in the new system will have many public keys that belong to the people they communicate with. So you'll pick, Bob will pick Alice's public key, use it to encrypt this message through this algorithm and send it out as a ciphered message. The ciphered message is received by Alice, and she can use her private key to decrypt the message. As you notice, her public key was used, Alice's public key to use to encrypt, and now Alice's private key is used to decrypt. Same person. Or think of this. Don't get yourself mixed up. If you encrypt the message with Alice's key, you can only use Alice's key to other key to decrypt it. And she can generate that key, that message. And if you want to send an authentic message, then there's the way to explain it. You take the plain text message and the algorithm, and you use the sender. This is Bob. Bob uses his private key. And once the message is encrypted, then Bob's other key need to be used. So when Alice receives the message, she must use Bob's key, Bob's public key. And don't just say Bob's key, you must say which of his keys, the private or the public. Say in an exam, if you explain it, but you don't say, here you say, Bob uses his key to encrypt the message. That's zero, that's no good. And the receiver, if you say, Alice uses Bob's key, then it's no good. You need to say Bob's public key. Now, sometimes, so remember, you either send a message that's confidential, nobody can read, or a message that can only be, you know who sent it, but it's not confidential. Because sometimes you don't want to, like there's so many documents that are sent from one place to another, they're not necessarily confidential, but you want to make sure it came from that right person. It's like if I send you an email and I say, don't worry, don't upload the solution to that assignment or that tutorial, you don't need to. I'm giving you the 10 marks for free. I'm signed Faheem, but it's actually, I didn't send it, someone else sent it to you. So you need to authenticate that. So sometimes you need a message to be both. You want to send it confidential, but if you receive a confidential message, you are never sure who sent it. Because anybody can take your public key, encrypt the message, send it to you, and sign it with any name. So yes, it's confidential. Nobody was able to read it except you, since the sender sent it. But you're not really certain who the sender is, because everybody has your public key, and everybody can take your public key and use it to encrypt a message and send it to you. And they put a different name underneath it. So it's not authentic. When you receive a confidential message, it doesn't mean you're certain of the sender. Now, on the other hand, if you receive a confidential message, if somebody used if you want to use an authentic message, the person has to use their private key and send it to you, and you can decrypt it using their public key, the sender public key. But it's not confidential. Everybody can get that message and can use the sender's public key and read it. Now, if you want to use both, if you want a message to be confidential and also authentic, then it needs to be encrypted twice by the sender. So it must be encrypted twice. Once encrypted by the sender's private key, so you can read it later on and be certain it's him, but then, or her, but then you have to encrypt that encrypted message, encrypt it again using the receiver's public key. And that makes sure then it's confidential. So if you need a message to be confidential and authentic, it has to be encrypted twice. And it has to be encrypted twice in the correct order. Encrypted by the private key of the receiver first, and then by the receiver's public key. Sorry, the private key of the sender, and then followed by the public key of the receiver. So here's what you need to do if you want to send a message that's both confidential and authentic. So if you're asked, how do you send a message in using public key encryption system that's authentic and confidential? We take the plain text message, that's A, from user A, and encrypt it using whose key? A's private key. PR here short for private, and A is this guy here, user A, or the sender. You can use S to indicate it's the sender. And that message, that encrypted message that we have, this message is encrypted again using the public key of the B user B, who is the receiver here. So we encrypt it first using the private key of the sender, then followed by the public key of the receiver, and send it out, and this is now the message. So this is the ciphered message. So this is the ciphered first cipher, and then ciphered again, C2. So the message is encrypted twice, and for the receiver to read it, they must also decrypt it twice, and decrypt it in reverse order. So this one, the second encryption happened using the public key of this guy, of B, the receiver. Now we use the private key of the receiver first to decrypt this message. And that will generate, so we use the private key of the receiver B to bring it back to the C1, the first encrypted message, which was encrypted by the sender's private key, and now we use the sender's public key, the public key of A, and that will bring back the message. So it's two encryptions. You need to physically know exactly and in the correct order. And the steps are written here so you can follow them from there. This was a question in a previous paper. So make sure you're okay with it. How do you actually encrypt a message or send a message that's both confidential and authentic using public key encryption system? Okay, so we'll be talking about digital signature. So is there something like digital signature? In the older days, you go to a bank and they give you a piece of paper and you sign, and they keep a copy of that signature, and they give you a checkbook. You write a checkbook and you sign it, and then somebody wants to withdraw the money, they compare the signature on the checkbook, on the check, with the signature they have in the bank, and compare them, and if they're happy, then they let you go. So what's so special about that signature of yours, your hand signature? Your hand signature is supposed to be easy to do by you, difficult for others. So you can sign because you're used to it. Maybe in the old days they probably signed thousands of times, then they're so used to signing, and if somebody tries to imitate it, they'll find it difficult. But there are specialists who can actually imitate it very easily. But it was safe enough. It was the only way to guarantee authenticity, was your signature. So, and also, it's easy to do, but it's hard for anyone to, and it's easy to verify. So if the bank, they have the original signature and they compare it, they can see it's pretty much the same. Even though, many people have sometimes forged signatures, and it actually went through the bank without detection. So, dependence on a message and a signer. This depends on the message and on the person who signed it. But in our digital signatures, we do pretty much the same thing. So it's encryption. You encrypt something with your private key, which no one else can do because they don't have your private key. And it's also easy to verify. If you want to know, did I really send this message? Is that my encryption, my signature? All you have to do, use my public key to decipher it. If it deciphers, that means yes, it was encrypted using my key. Because my public key is the only number or key in the world that can decipher that message if I use my private key. Remember those two keys? One of them can lock. There's no other key to unlock except the other one, the private. And I told you this is my public key. Then if you can use it to decipher a message, that's a proof that it was encrypted by me. And that's where authenticity comes in, or digital signatures come in. But what's the problem with public key? Anybody knows what is the disadvantage of public key encryption system? It seems to provide everything. Encryption. It provides confidentiality. It provides authenticity. It provides digital signature. Provides non-repudiation. Well, what's the problem with it? What's the disadvantage of public key? No, What's the disadvantage of public key encryption system?
It may need a server to distribute.
Thank you. That's an advantage. A disadvantage. I'm looking for disadvantage of public key encryption system.
Too slow?
Slow. That's the disadvantage. It's probably the only disadvantage. This is the major disadvantage. It's too slow to encrypt large files. And therefore, there's a twist to digital signature. We'll look at it another time. But it's a slow operation. So one problem with symmetric key algorithm is that the sender needs a secure method of telling the receiver key or of the receiver's key. Plus, you need to separate key from everyone else you might communicate with. That's with the symmetric systems. Yeah, okay. Key distribution is a problem with symmetric systems. Public key algorithms use public key and private key pair to tackle the key management problem. And each receiver has a public key pair, and the public key is publicly known, it's published, and the sender uses the receiver's public key to encrypt. Okay, we've already gone through all that. Public key encryption system, its history. It was first proposed by Diffie, Whitfield, Diffie, and Martin, or Martin Hillman and Whitfield Diffie. So Diffie and Hillman are two famous mathematicians that thought of this a long time ago, back in 1976. And a crucial feature is that the private key is difficult to determine from the public key, and generally, these algorithms are much slower than symmetric key. But these guys, their names, Refset, Shamir, and Edelman, they actually came up with the first implementation of public key encryption system. And they called it with the first name of each one of them, RSA. And that became the name RSA, the first character of their names. So, and this is how it works. This is how the pair of keys, how the keys generate, how we generate the public and private key. And you need to know how this works. Okay, so I'll leave the mathematics out of it, just look at it now briefly and let's see how it makes sense. So you need to start with two numbers. Two numbers that are prime numbers. So in this example, we look at two prime numbers, P and Q. So they have to be prime numbers. And they have to be large, but we've used the smallest prime numbers we can use, just to keep calculations to a minimum. So now we have a pair of keys or a pair of prime numbers, and we need to generate one of the first key. Remember now something else you need to know is that the actual key, when we say the key actually consists of two numbers. When we say the encryption key, is that you get two numbers that make one key. And in fact, in this case, we need to create two. The pair of keys that we say one of them is public key and one is private. This is one of the keys, 3 and 15, and this is the second key, 11, 15. So every key, remember we said every person has to have two keys. Now every key consists of two numbers, not one number. And this is a very simple and small example of the two keys, 315 and 1115. And the two numbers, as you can see, that make up each key, they're actually common in one of the numbers. So the second number in every key is the same. But still, you can't say my key is 3. You have to say 3 and 15, or call both numbers to make up the key. Right. Now, so this common part is created by multiplying those two prime numbers together. So this prime number 3 and 5, if they're multiplied together, we create the number n. And that's really n, this part here, the 15, we refer to it as n. There it is, en and dn. So we're so easy, quick to produce, at least the n part of the key. So you get any two prime numbers, let's say you got, I don't know, 37 and whatever the other prime number is, 61 prime number maybe. And you multiply them together and you get this part of the key. Now we need to produce the other two numbers, the 3 and the 11, to finish. Now, we start with one of them. First, they say you need to produce another number that consists of p minus 1 and q minus 1. So p started at 3, minus 1 is 2, and the q, which is 5, minus 1 is 4, and multiply them together and you get the number 8. Now this number 8, we need two co-prime numbers that kind of are common with number 8. And when we say co-primes or relatively primes, that means they don't necessarily be primes. Ideally they should be primes, but co-primes, that means that's just those two will have no common divisor. So at least to one another, they seem to be like relatively prime to one another. For example, maybe 9 and 10. Like there's no other number that divides by that's a common, or they have no factor that's common to the two of them. The 9 doesn't divide by 2, the 10 divides by 2, but 3, the 9 divides, but the 10 does not divide, so they don't have a common factor between them. And therefore we can say to one another, in relation to one another, they're like prime numbers, even though they may not necessarily be prime as in the bigger picture of prime. But they call them relative primes. That means if two numbers are relatively prime, they have no common denominator. So, let's keep that idea. So we got the M8 now. All we have to do is work with the E. We start with the E, and the E we can have any option. It has to be an odd number. There are a few conditions, but there'll be so many numbers there, and it has to be odd and prime. And we can have a long list of them, and we pick one of them. We pick the smallest one. And it has to be less than 8, less than M in this particular case. We use very small numbers. So that's it. That's the E is also easily created. Now this is the little one with the slight difficulty, but so you can actually create those numbers very quickly. But let's look at the D. So the D has to be prime number with E, with the 3. Those two numbers have to be prime numbers. Well, how do we get it? In relation to M, they say if you multiply D and E and mod the number by M, divide it and get the remainder should be 1. I don't know if you remember, we looked at that briefly in the past. We'll talk more about it in the future. This fact that if two numbers are multiplied together and modded by another number, if the result is 1, remember we done it in one of the encryption algorithms to find the relative prime when we were doing the matrix determinant or something. Anyway, forget about that, don't worry about it. This, if you find any two numbers that multiply and modded, say, by a common number, that's 8, you get the remainder is 1, then they are co-primes and they will be good keys together. So now we have the 3. All we have to do, find what other number, you multiply it into 3 and mod it by 8, you get you the result of 1. That would be a good candidate. So whatever way we do it, there are many different ways, but I thought I'd lay it out here. So start with all the numbers from 3, 4, 5, 6 and all that. So we have E is 3, multiply it into 3, you get 9. 9 divided multiply 8 gives us the remainder of 1, which is good. That's the first number, but that's the same number, 3. There's no, we can't have 3 and 3, it's not good. Let's try then 4. We multiply 3 times 4 is 12, multiply 8 is 1, and the remainder is 4, so it's no good. You take the next number, and you keep going. 3 times 5 is 15, multiply 8 gives you 7, the remainder. 6, 3 times 6 is 18, so these are I'm just trying all the numbers, 3, 4, 5, 6, 7, and each one of them multiplying to e, give me that number, and I keep going, and dividing by 8, and I find when I get to 33, that multiplies by 8 with the remainder of 1. So that's another possibility. Another possible number, 11, and so on. So, and you can keep going, and you find, usually when we use large numbers, we'll find a few, or many of them, that numbers that will multiply into the first number we picked, multiply m, and give us a remainder of 1. And that will be another candidate. So we can pick 3 or 11 or whatever other numbers that we come up with. And it has to be less than n. It cannot be bigger than 15 in this case, but usually 15. If we start with big numbers, that number will be huge as well. So once we find one of them, let's say we found the 11 and the 3, so we'll use the 11. So that's the D. So now E and L, that's 3 and 15, or E and N, that's 11 and 15, these are the 2 keys. One can be a public key and one can be a private key. So this is exactly the algorithm of the technique, but it's used in bigger numbers. This is on smaller, just to get the idea. So it can easily be programmed. Probably one of the most difficult parts to program it is the first part, is to start with 2 prime numbers. So you need a list of prime numbers between 1 and whatever the biggest number, you can decide whatever the largest number you can have. But luckily you can only do it once and save all these prime numbers somewhere. Anytime now you want to create a new pair of keys, you can pick randomly from this list of prime numbers, any 2 numbers, bring them and start using them. So that would be the you need an algorithm or special algorithm to generate prime numbers. But once that's created in a list, you can then just pick any 2 numbers from the list and use them to create a pair of keys. So now let's try them out. How does the encryption system work? How do you encrypt numbers using one of the keys? And now the numbers, again, are all any message. You look at the byte, you want to encrypt it, you look at the byte as a numerical value. So everything is numeric here. Well, let's say we want to encrypt number 7. This is the data we want to encrypt using one of those keys. So how does it work? To encrypt a number, a cipher message, I have the formula here, is the data at 7 to the power of E. If we're using this key. If we are using this key, it will be to the power of this, whichever key you want to use. It doesn't matter which key. And here, by mistake here, they keep calling one of them EN and the other one DN. E to mean encryption key and D decryption key, which is not very accurate. Because any key can be used for encryption, any key can be used for decryption. They should have used different names for that. But anyway, it doesn't matter. We have a pair of keys. These are the pair of keys, and every key consists of 2 numbers, and the second number. And some textbook, they actually write them in reverse. They write the common number first. Doesn't matter. Most books use the common number as the last. Now, you take the first number, the data, and to the power of 3, and multiply the second number, which is 15. So, to do that, 7 multiplied by itself 3 times, which is 333, multiplied by 15, and it gives us the remainder 13. And that's the cipher character. So the number 7 is encrypted using this key to give us 13. Now, To decrypt it, you do exactly the same algorithm, but you use this key. So you have the 13, you want to decrypt it. You say the data is 13 to the power of this part of the key, the first key, which is the power of 11. 3 to the power of 11. It's a big number. As you can see now, you can see it's why it's slow. Because we can be talking about number 300, for example. 13 to the power multiplied by itself 300 times. And mod it each time, but because you can't, even when you write this is so easy to program it. But if you program it in such a way, you say, give me the result of this, 13 multiplied by itself 11 times, you'll run out of memory in your computer. So, as a programmer, what you should do is do this once. Multiply 3 by itself, 13 times 13, mod by 15, divide. So it'll give you another number less than 15. And then multiply that by itself one more time until you finish 11 times. And each time you do it, mod it, so to keep the number small all the time. It'll give you the same result. Especially when you go to big numbers like 370, for example, the key here. Multiply a number here, and this number can be 200. Any ASCII code we use. So if the number is 200 multiplied by itself 370 times, you don't have space in memory. No computer will be able to do it. But you multiply by itself once and modify the end, the 15. And then multiply it again and multiply and mod. So you do the whole thing 300 times instead of this 300 times and then mod it once. And therefore, you have a multiplication and a modding, and you have to do that 300 times, the two of them, to each character, to each part. But anyway, that's how it's done. It's simple, it's easy, you can program it. And when you work out all this result, you get back 7. And you could be asked to give an example to create a key, and that would be a nice example, to create a pair of keys for RSA, or you can be given a key and you say, okay, use this key to decrypt this message, and you're given a number, and this is the calculation you need to do. So, obviously, if you ever get this to the exam, the numbers will be reasonably small. You won't be getting large numbers. So this is the key generation kind of algorithm, just summarized. You need 2 prime numbers, P and Q. Here we just call them P and Q. Create N. N is multiplied, the result of the product of P multiplied into Q. You get N. And N, that's part of the both keys. The second number in each of the keys, the private and the public key. And then choose a small number E that's co-prime to M. Okay, I forgot to mention the M bit. So you create M, and M is the next number below P and Q. And just to let you know, the next number less than P is prime with P as well. Because any prime number, let's say, give me a prime number 11. The number below it is 10. It can never have common denominator with 11, because 11 is prime anyway. Every number below it does not divide by it, or else it wouldn't be prime. Okay, a prime number, it divides by no other number except by itself or 1. So any prime number, say 23, if you go to the one below it, 22, is co-prime with that 23, because we know 22 will never divide by 23, or have a common divisor, or otherwise 23 wouldn't have been a prime number. All the numbers below 23 are co-primes with 23. We need those ideas for later on, but okay, so that's why they pick P minus 1 and Q minus 1, because those two numbers that we get are co-primes to P and Q. And then once we got the M, then we choose a number E such a way that's a small number, and smaller than N, and co-prime with M. And once we get that number E, then we will calculate what D is, and D has to be Again, if you multiply D and E and multiply M, the result should be 1. And then you publish the key. One of them D and N, and the other is E and N. Even though it doesn't, oh yeah. So as you can see, it's quite simple, and I hope you do. This is a bit more details. Finding two prime numbers, P and Q, multiply them together, you get the N, and multiply P minus 1 and Q minus 1 to get the M. So we already got one step or two steps, the N and the M. Now, these are the conditions for E. There was an exam question once, so what are the characteristics or conditions required in the E part number of the key generated? E has to be greater than 1. You cannot have 0 or negative numbers. E has to be less than N, as far as I know, but this one say, yeah, P and Q. So P and Q multiplied together is known as N, or the two prime numbers multiplied together. So E that we use has to be smaller than N, it has to be bigger than 1. And E and M are relative primes, which means they have no prime factor in common. So E and M, they have to be co-primes. E doesn't have to be prime by itself, but as far as M is concerned, in relation to M, it has to be prime or co-prime. E does not have to be prime, but it must be odd. E must be an odd number, greater than 1, and less than N, and co-prime with M. So these are the conditions for E. And then compute, once you get the E, then compute the D now, in such a way that E multiplied into D multiplied by M equals 1. Mathematicians can write it in many different ways, but D times E equals 1 if multiplied by M. That's the way they read it, but whichever way you come up with, it's as long as it gives the same meaning. And they call D the multiplicative inverse of E. So E and D are inverse of one another. That's what we did when we did Hill cipher. We needed to get the inverse. This is easy to do. Simply find an integer x which causes whatever it is. This is another way of writing it, but it actually means write D and E multiplied by M equals 1, or M plus 1 can be divided by either one of the numbers to be an integer, and then use that value as D. So now once you created the D and the E, to encrypt, to cipher a message, the cipher equals, you take the message to the power of E and multiplied by N. This is the formula. And for the decryption, to generate a plain text message equals the ciphered message to the power of D. Now remember, D and E can be reversed here, but multiplied by N. That's why I'm saying we shouldn't be using those. It's wrong to use E and D here because you don't know which one is which key we're going to be using. We can use either key for encryption. Okay. I think we need to quit at this stage. I was going to give you an example to work it out, but I'll give you a small one. No. I think we'll finish the rest of it at the next lecture. Any questions? Right, just one quick question. What did I not ask about? Right, I'm going to ask you to send me a message. That's confidential.
I use your public key. I use your public key to encrypt it. You use your private key to encrypt it.
Okay, very good. You combine the receiver's public key to encrypt the message, and the receiver should use the receiver's private key to decrypt it. That's confidentiality. What about authenticity? You want to send me a message, but then you know it came from you, not from someone else. To decrypt it. Okay? All right, I got perfect answers. I had a couple of pens I wanted to give away, but I'm going to let you go home early today. And I'll see you next week. Let's make sure the attendances work first.